Hello and welcome to the third part of the training program on fan and blower. I am Neha. Hope you have learned thoroughly about fan and blower and its parts in the previous modules. In this module, we will learn about its performance and characteristics. In the end of the module, you will be able to explain about fan performance assessment, define static, total, and velocity pressure measurement, explain velocity pressure or velocity calculation, explain air density calculation and velocity calculation, describe fan efficiency, explain the system characteristics, describe the fan characteristics, explain about fan performance with outlet damper and variable speed, describe fan laws, explain fan design and selection criteria. Learned in detail about fan and blowers in the previous modules. Let's begin with fan performance assessment. To have a better understanding of fan performance, it's important to learn about some terms associated with it. Let's look at it. Static pressure. Static pressure is the measure of the potential energy of a unit of air in the particular cross-section of a duct. Air pressure on the duct wall is considered static. Imagine a fan blowing into a completely closed duct. It will create only static pressure because there is no airflow through the duct. Static pressure is the resistance to airflow, friction, caused by the air moving through a pipe, duct, hose, filter, or air control dampers. Dynamic pressure. Dynamic pressure is the kinetic energy of a unit of airflow in an airstream. Velocity pressure is the pressure along the line of the flow that results from the air flowing through the duct. Dynamic pressure is a function of both air velocity and density. The static and dynamic pressures are mutually convertible. The magnitude of each is dependent on the local duct cross-section, which determines the flow velocity. Total pressure. Total pressure is the sum of the static and velocity pressure. Velocity pressure and static pressure can change as the air flows through different sized ducts, accelerating and deaccelerating the velocity. The total pressure stays constant, changing only with friction losses. Do you have any idea how fan flow is measured? If no, let's learn about it. The fan flow is measured using 1. Pitot tube, manometer combination, or 2. A flow sensor, which is a differential pressure instrument, or 3. An anemometer. Moreover, care needs to be taken regarding number of traverse points, straight length section, to avoid turbulent flow regimes of measurement upstream and downstream of measurement location. The measurements can be on the suction or discharge side of the fan, and preferably both where feasible. Now, let's look into details of measurement by pitot tube. How does one measure velocity pressure using a pitot tube and a manometer? Total pressure is measured using the inner tube of pitot tube and static pressure is measured using the outer tube of pitot tube. When the inner and outer tube ends are connected to a manometer, we get the velocity pressure. For measuring low velocities, it is preferable to use an inclined tube manometer instead of U-tube manometer. For calculating the velocity pressure, the following points must be kept in mind. When measuring velocity pressure, the duct diameter or the circumference from which to calculate the diameter should be measured as well. This will allow us to calculate the velocity and the volume of air in the duct. In most cases, velocity must be measured at several places in the same system. The velocity pressure varies across the duct. Friction slows the air near the duct walls, so the velocity is greater in the center of the duct. The velocity is affected by changes in the ducting configuration, such as bends and curves. The best place to take measurements is in a section of duct that is straight for at least 3 to 5 diameters after any elbows, branch entries or duct size changes. To determine the average velocity, it is necessary to take a number of velocity pressure readings across the cross-section of the duct. The velocity should be calculated for each velocity pressure reading and the average of the velocities should be used. Do not average the velocity pressure, average the velocities. For round ducts over 6 inches diameter, the following locations will give areas of equal concentric area as shown in figure. For best results, one set of readings should be taken in one direction and another set at a 90-degree angle to the first. For square ducts, the readings can be taken in 16 equally spaced areas. If it is impossible to traverse the duct, an approximate average velocity can be calculated by measuring the velocity pressure in the center of the duct and calculating the velocity. This value is reduced to an approximate average by multiplying by 0.9. Now, we are going to learn some important terms and terminology and the associated formulae. Air density calculation. The first calculation is to determine the density of the air. To calculate the velocity and volume from the velocity pressure measurements, it is necessary to know the density of the air. The density is dependent on altitude and temperature. The formula for gas density can be expressed as follows, where T refers to temperature of gas or air at site condition in degrees Celsius. Velocity calculation. Once the air density and velocity pressure have been established, the velocity can be determined from the equation as displayed on screen, where Cp denotes pitot tube constant 0.85 or as given by the manufacturer. Delta P denotes average differential pressure measured by pitot tube by taking measurement at number of points over the entire cross-section of the duct. Gamma denotes density of air or gas at test condition. The volume in a duct can be calculated for the velocity using the equation as displayed on screen, where Q denotes volumetric flow in meter cube per second. V denotes velocity in meter per second. Fan efficiency. A manufacturer generally uses two ways to mention fan efficiency. Mechanical efficiency, sometimes called the total efficiency, and static efficiency. Both measure how well the fan converts horsepower into flow and pressure. The equation for determining mechanical efficiency is displayed on screen, where eta mechanical denotes percentage of mechanical efficiency. Delta P denotes total pressure in millimeters water column. mmWc denotes millimeters water column. kW denotes kilowatt. The static efficiency equation is the same, except that the outlet velocity pressure is not added to the fan static pressure. It can be expressed as shown on screen, where eta static denotes percentage of static efficiency. Delta P denotes total pressure in millimeters water column. mmWc denotes millimeters water column. kW denotes kilowatt. Drive motor kilowatt can be measured by a load analyzer. This kilowatt W multiplied by motor efficiency gives the shaft power to the fan. Now we are going to learn some important terms and terminology and the associated formulae. Next, we'll be discussing the topic system characteristics. The term system resistance is used when referring to the static pressure. The system resistance is the sum of static pressure losses in the system. The system resistance is a function of the configuration of ducts, pickups, elbows, and the pressure drops across equipment, for example, bag filter or cyclone. The system resistance varies with the square of the volume of air flowing through the system. For a given volume of air, the fan in a system with narrow ducts and multiple short radius elbows is going to have to work harder to overcome a greater system resistance than it would in a system with larger ducts and a minimum number of long radius turns. Long narrow ducts with many bends and twists will require more energy to pull the air through them. Consequently, for a given fan speed, the fan will be able to pull less air through this system than through a short system with no elbows. Thus, the system resistance increases substantially as the volume of air flowing through the system increases, square of air flow. Conversely, resistance decreases as flow decreases. To determine what volume the fan will produce, it is therefore necessary to know the system resistance characteristics. In existing systems, the system resistance can be measured. In systems that have been designed but not built, the system resistance must be calculated. Typically, a system resistance curve, as displayed in figure, is generated with for various flow rates on the x-axis and the associated resistance on the y-axis. Assume a fan with a fixed duct system. An adjustable damper is installed in the ductwork upstream of the fan. Assume that these dampers are adjusted according to requirement. As the system resistance increases, the curve shifts towards left. As the damper is closed, the system resistance increases. The following figure of pressure versus flow rate shows a system curve with damper wide open, 3/4 open, half open, 1/4 open, and fully closed conditions. Next, we are going to learn about fan characteristics. Fan characteristics can be represented in form of fan curves. The fan curve is a performance curve for the particular fan under a specific set of conditions. The fan curve is a graphical representation of a number of interrelated parameters. Typically, a curve will be developed for a given set of conditions, usually including fan volume, system static pressure, fan speed, and brake horsepower required to drive the fan under the stated conditions. The intersection of the system curve and the static pressure curve defines the operating point. When the system resistance changes or the flow rate changes, the operating point also changes. After having learned the fan characteristics, let's move ahead and learn about fan performance. We'll start with fan performance with outlet damper. As the flow rates decrease, the fan curve shifts towards left. As the dampers close, the flow rates decrease accordingly. The following figure of pressure versus flow rate shows fan performance curve of a system curve with damper wide open, 3/4 open, half open, 1/4 open, and completely closed conditions. Continuing with the topic, fan performance. Next, we'll look at fan performance with variable speed. Flow rate also depends on fan RPM. As the flow rates decrease due to variable speed, the fan curve shifts downwards. As the RPM decreases, the flow rates decreases accordingly. The following figure of pressure versus flow rate shows fan performance curve of a system. For a system such as ABCD, performance will be at A at full speed, B at 3/4 speed, C at half speed, and D at 1/4 speed. Learnt about fan curve and system curve. Both these curves can be shown on static pressure versus flow rate as shown in the graph. Let us now understand system characteristics and fan curves through a graph. In any fan system, the resistance to airflow or pressure increases when the flow of air is increased. As mentioned before, it varies as the square of the flow. The pressure required by a system over a range of flows can be determined and a system performance curve can be developed. It is shown as SC in the image. This system curve can then be plotted on the fan curve to show the fan's actual operating point at A, where the two curves N1 and SC1 intersect. This operating point is at airflow Q1 delivered against pressure P1. A fan operates along a performance given by the manufacturer for a particular fan speed. The fan performance chart shows performance curves for a series of fan speeds. At fan speed N1, the fan will operate along the N1 performance curve as shown in the image. The fan's actual operating point on this curve will depend on the system resistance. Fan's operating point at A is flow Q1 against pressure P1. Two methods can be used to reduce airflow from Q1 to Q2. First method is to restrict the airflow by partially closing a damper in the system. This action causes a new system performance curve SC2, where the required pressure is greater for any given airflow. The fan will now operate at B to provide the reduced airflow Q2 against higher pressure P2. Second method to reduce airflow is by reducing the speed from N1 to N2, keeping the damper fully open. The fan would operate at C to provide the same Q2 airflow but at a lower pressure, P3. Thus, reducing the fan speed is a much more efficient method to decrease airflow since less power is required and less energy is consumed. The fan operates under a predictable set of laws concerning speed, power, and pressure. Let's learn in detail the fan laws. A change in speed or RPM of any fan will predictably change the pressure rise and power necessary to operate it at the new RPM. Fan laws are the equations which help to predict with good accuracy the performance of a fan at other speeds and densities than those of the original rating tests. It is not practicable to test the performance of every size of fan in a manufacturer's range at all speeds or densities at which it is to be used. For the same fan, the dimensions get fixed and the laws are Q1 upon Q2 is equal to N1 upon N2. H1 upon H2 is equal to N1 upon N2 whole square. P1 upon P2 is equal to N1 upon N2 whole cube. For the different size and other conditions remaining same, the laws are Q1 upon Q2 is equal to D1 upon D2 whole cube. H1 upon H2 is equal to D1 upon D2 whole square. P1 upon P2 is equal to D1 upon D2 whole to the power 5. For the same fan, discharge is directly proportional to speed. Head developed is directly proportional to square of speed. Power is directly proportional to cube of speed. For the fans of different sizes, discharge is directly proportional to cube of diameter. Head developed is directly proportional to square of diameter. Power is directly proportional to fifth power of diameter. We have learnt about the fan laws. Are you aware of the fan designs? And what about the various selection criteria? If not, let's learn about it. Precise determination of airflow and required outlet pressure are most important in proper selection of fan type and size. The airflow required depends on the process requirements, normally determined from heat transfer rates or combustion air or flue gas quantity to be handled. System pressure requirement is usually more difficult to compute or predict. Detailed analysis should be carried out to determine pressure drop across the length, bends, contractions, and expansions in the ducting system, pressure drop across filters, drop in branch lines, etc. These pressure drops should be added to any fixed pressure required by the process. Once the system flow and pressure requirements are determined, the fan and impeller type are then selected. For best results, values should be obtained from the manufacturer for specific fans and impellers. The choice of fan type for a given application depends on the magnitudes of required flow and static pressure. For a given fan type, the selection of the appropriate impeller depends additionally on rotational speed. Speed of operation varies with the application. High-speed small units are generally more economical because of their higher hydraulic efficiency and relatively low cost. However, at low pressure ratios, large, low-speed units are preferable. There are certain requirements for an energy-efficient fan system. Let's look at what are they. First, choose the right fan. Second, reduce the system resistance. Third, operate close to BEP. Fourth, maintain fans regularly. Fifth, control the fan airflow. Click on each point to know more about them in detail. First point is regarding choosing the right fan. Following are the considerations for fan selection: noise, rotational speed, airstream characteristics, temperature range, variations in operating conditions, space constraints and system layout, purchase or operating costs and operating life. Systems approach is the most important. Avoid buying oversized fans due to following reasons. Do not operate at best efficiency point. Risk of unstable operation. Excess flow energy. High airflow noise. Stress on fan and system. Second point we are going to discuss is reducing the system resistance. Increased system resistance reduces fan efficiency. Check periodically. Check after system modifications. Reduce where possible. Next thing we need to ensure is that operating the fan close to BEP, which is best efficiency point. Best efficiency point is equal to maximum efficiency. Normally close to rated fan capacity. Deviation from BEP results in inefficiency and energy loss. Next point is maintaining the fan regularly. It includes the following steps to be followed. Periodic inspection of all system components. Bearing lubrication and replacement. Belt tightening and replacement. Motor repair or replacement. Fan cleaning. The next point we need to keep in mind for an efficient fan system is controlling the airflow. The fan airflow can be controlled using the following means: pulley change, dampers, inlet guide vanes, variable pitch fans, variable speed drives (VSD), operating fans in parallel, operating fans in series. Click on each to know more about them. Pulley change, reducing the motor or drive pulley size. Following are the advantages and disadvantages. Advantages: permanent speed decrease, real energy reduction. Disadvantages: fan must handle capacity change. Only applicable with V-belt system. Dampers, reduce flow and increase upstream pressure. Following are the advantages and disadvantages. Advantages: inexpensive, easy to install. Disadvantages: limited adjustment, reduce flow but not energy consumption, higher operating and maintenance costs. Inlet guide vanes. Following are the advantages and disadvantages. Inlet guide vanes improve efficiency, swirls in fan direction, load and airflow. Cost effective at 80 to 100% of full airflow. Disadvantage: less efficient at less than 80% of full airflow. Inlet guide vanes. create swirls in fan direction, reduce angle air and fan blades, lowering fan load, pressure, airflow. Operate more fans in parallel instead of one large fan. When two fans are installed side by side in such a way that they draw air from the same source and deliver it to the same destination, they are said to be in parallel. When two fans are connected in parallel, they may not handle the same quantity of air. However, they produce the same pressure as they are drawing air from a common point and also delivering it to a common point. Advantages: high efficiencies at varying demand. Risk of downtime avoided. Less expensive and better performance than one large fan. Can be equipped with other flow controls. Disadvantage: only suited for low resistance system. Variable pitch fans changes angle in coming airflow and blades. Following are the advantages and disadvantages. Advantages: high efficiency at range of operating conditions. No resonance problems. Disadvantages: applicable to axial fans only. Reduced efficiency at low loads. Operate more fans in parallel instead of one large fan. When two fans are installed side by side in such a way that they draw air from the same source and deliver it to the same destination, they are said to be in parallel. When two fans are connected in parallel, they may not handle the same quantity of air. However, they produce the same pressure as they are drawing air from a common point and also delivering it to a common point. Advantages: high efficiencies at varying demand. Risk of downtime avoided. Less expensive and better performance than one large fan. Can be equipped with other flow controls. Disadvantage: only suited for low resistance system. Variable speed drives. Following are the advantages and disadvantages. Advantages: most improved and efficient speed control. Speed adjustments over continuous range. Variable speed drives reduce fan high costs. Variable speed drives reduce fan speed and airflow. They are of two types: mechanical VSDs, electrical VSDs. Operate fans in series. When two fans are installed one behind the other in such a way that they handle the same air, they are said to be in series. When two fans are in series, the same volume of air passes through each, and each adds a certain amount of pressure to it. In the process. Advantages: lower average duct pressure, less noise, lower structural or electrical support required. Disadvantages: not suited for low resistance systems. Having learned about both operating fan in series and operating fan in parallel, let's compare the fans. Two fans in parallel will produce double the free flow of one. Fans in series increase the shutoff pressure to twice that of a single device. Note that at intermediate flow points, the flow and pressure increases, and whether fans should be in series or parallel depends upon the degree of system resistance. After having learned the series and parallel combination, let's sum up what happens when multiple fans are used. When applying more than one fan in a system, N fans in series will increase pressure N times at a given flow rate with no additional flow rate. Fans in series can be useful in high resistance systems. N fans in parallel will increase flow N times at a given pressure level with no additional static pressure generated. Fans in parallel can be useful in low resistance systems. Now that you have completed the module, don't you think that it's necessary for you to check your knowledge by answering these questions? So let's go ahead and take a small test on this module.